Hello, I'll be explaining the damn harmonic oscillator and its three stages, which are the critical damping, the underdamping, and the overdamping. To start, what is a system of damp harmonic oscillation? A system of damp harmonic oscillation, it's a system where there's like a particle, let's say a particle, and the most common example is a spring. So the spring, it's going to do this movement, dissipating its energy. Like you pull it like this, and it starts going like this, dissipating the energy until it gains to the equilibrium position. Or yes, it's equilibrium position, but it doesn't move, right? Where all the forces are cancelled. So that's basically the damped harmonic oscillation. But it has many state. It has three states. The critical damping, it's a state where it goes. It tries to return as quick as possible to the equilibrium position. So the critically damped state, maybe once or twice will overshoot or get over the equilibrium state, maybe one, two times, but it will return quickly to that equilibrium position. While the on the damped uh, on the damping, it's going to do basically lots of going up and down into the equilibrium position until it gets to the equilibrium position. Obviously, it's going to take more time, but uh, yes. Now the overdamped uh, uh, state, it's really similar to the critical damping. The critical damping, you remember, it's going to get as quickly as possible to the equilibrium position, but the overdamped, it's going to take longer. It's going to take longer time to get there to that equilibrium position. I actually got a video to show you how a system of this works. So let me get to the video. Hey, it's made by this YouTube channel called Forest Charnock. So let's see it. So this is the system. Look at it. It wants to go back to the equilibrium position, and here it gets to it to that equilibrium position. Now, what happens when the damp increases? Well, here we can see that if the damp increases, it's going to be uh, need less time to get to that equilibrium position. So this correlates to the program we did on MATLAB. Let me show it to you. I show how does it work. Here it is. Uh, so let me run it. It will create a graph where we can see the states of damp harmonic oscillation. Here it is. As I said, to critically damped, it's always going to get quickly to the equilibrium position. While the over damped, it's going to get a little bit slower to that equilibrium position, but it's going to get there. Every single state here is going to get over there, but these are different just states, really. Here on the underdamped, we can see that it oscillates first over the equilibrium, under the equilibrium, then over the equilibrium, and we can keep imagining that it goes like this, like until it gets to the equilibrium position. Now, uh, something interesting I really like about this program, it's are these definitions where the damping ratio, it's going to explain us. It is other way of explaining the underdamped, overdamped, and critically damped. If the damping ratio is less than one, it's going to be underdamped. It's if it's overdamped, it's the damping ratio is going to be over one. And if it's critically damped, the damping ratio is going to be equal to one, which we can see here. As you can see, it's the same definition. So how does this code work? Well, we need these variables here to get to the one for the overdamped and one to the underdamped. Here we have value omega. Here we have above damp. This line starts going to determine our line, how the lines are going to be. Now these are plots. These plots are going to plot inside here. But how does he do it? Well, these are some functions we've got here. So let's get here. So over this is going to get this equation, which is actually over here, as you can see. It's all of this equation. And you can see the plot of this individually. And it's going to get our time, our variables of time of omega and z over, which is pi, and it's going to put them in a range of 0 to t, which is 2 times pi, which will be this over here. And it basically does the same with the under, obviously with the under variable and with critical, but here we don't have like critical variable for this. Why? Oh, because it just will go to 0. So here it is. Here is the formula for critical. As you can see right here, it's the formula for underdamped. Let me see if I can. Here it is. Now, these are just to make the graph, right? These texts are to get here the lines, the names. Overdamped, critically damped, underdamped. And here is their position. Now here on the grid on, we can make a label and an other while label, which will be these ones. Omega, amplitude, these are the labels. Uh, here we can also see the legends, which are the ones right here. These are the legends. The labels of the X component and the labels of the Y components. Here they are. So this is basically the explanation of the code.